All right, so we are talking about solubility equilibrium today, 18.4. The objectives here are to define the solubility product constant, KSP, to write different KSP expressions for the solubility of slightly soluble salts. Very important distinction there. And then to calculate the KSP for a slightly soluble salt in particular. So walking out of here today, you can explain what KSP represents and what equilibrium systems they apply to. You can, if you are given the name or formula for a slightly soluble salt, write the dissociation equation and the KSP expression. Remember, we've done dissociation equations already, and we've done K expressions already, but we just did KEQ. Now we're going to do KSP. And then if we give you the solubility of a slightly soluble salt, you can calculate its KSP. Okay, so just a reminder that when we talked about saturated versus unsaturated solutions and we talked about concentration, we do not have saturated solutions being the same thing as concentrated solutions. Remember, you could have something that's completely saturated, can't dissolve any more in it, but it might have just barely anything in there. Okay, or I could have something that has a ton of material dissolved in it, maybe some sodium acetate or something, right? Something that takes a ton of stuff and dissolves it all in there, but then there could still be room for more because it's not saturated yet. And so remember that saturated and concentrated are not the same thing, okay? We do measure concentration in the molarity units, right? And when we talk about our solubility equilibria, we're going to remember that that does not have a unit. So we did these dissociation equations before. We take a solid salt, right? And we dissolve it in water and we create some aqueous ions that dissolve in water, right? That's your dissociation equation. The solid breaks up into the two aqueous ions. In a pictorial format, we start with a bunch of little crystals at the bottom and they start to dissolve, and water basically is coming at them and pulling them into the solution. Eventually, you might get to a point where some of those particles of the aqueous component are coming back into making the crystal. And eventually, after that, you're going to get to a point where you've reached equilibrium, where you have an equal number of particles that are coming out of the solution as you do that are going back in or out into solution as you do going back into the crystal. So equal particles doing the leaving and the coming back, right? The leaving and the coming back. And so when you get to that point, you are at equilibrium. And that's where this double-sided arrow comes into play, right? So we are at equilibrium in terms of dissolving, solubility, okay? And so we're going to come up with what we call the solubility product constant to tell us where do we sit in equilibrium position with different chemicals and how they dissolve. So some chemicals will dissolve really easily, some chemicals will not dissolve, and this number can tell us kind of how well they dissolve, okay? All right, so our KSP is our equilibrium constant for the dissolving of a salt. We can get a number that will tell us our equilibrium position. Are we close to 1? Are we really low and very far away from 1? Ones that are close to 1 are probably dissolving pretty well. Ones that are less, really far away from 1 probably are not dissolving very well, okay? So we want to remember that this only applies to slightly soluble salts. Now, this is the stuff where before we basically said it was insoluble. Like if we looked at this solubility table that was up here on the whiteboard, we see that the values that we are considering now are the ones that up here were called insoluble, okay, or low solubility. So where they would actually form the precipitate, right? So the values that we're dealing with when we talk about KSP are for the stuff that doesn't dissolve. But what we're saying is it actually does dissolve just a tiny, tiny little bit, okay? And how much tiny, tiny little bit, that is going to be something that KSP helps us to see. All right, so in this particular example with calcium fluoride, I've got calcium fluoride solid breaking into calcium ions and fluorine ions. Now, you can write the KSP for that. Just like we wrote KEQ, it's the products divided by the reactants. So my two products here, Ca2 plus and 2F minus, they are going to be on the numerator. Remember that the fluorine ion here has a 2 exponent because it has a 2 coefficient. So this 2 exponent, remember, is because of our 2 coefficient that's here. Now, there are no values in the denominator. All we have is the numerator. Why is there no value in the denominator? Let's go with, remember your element name, gallium. Yeah, right. Remember that when we do our K values, we cannot include any solids in our final values, right? And so we have to make sure that we don't have solid here. Ooh, gunpowder. Congratulations, gallium. All right. So that's why we are not including that in our equation. And that means that all of these solubility product constant values will always just be the numerator, right? Just the reactants multiplied by each other, because none of these types of equations are going to have reactants that are not solid, because they're always little crystals, little solid little crystals that we put in and dissolve, right? All right. So if we were going to write the equilibrium equation or the KSP expression for these things, we would first write our dissociation equation. So we'd start with our AgCl as a solid, and it's going to break into our Ag plus as an aqueous, plus our Cl minus as an aqueous. And then we could write our KSP for that. And we'd say our KSP is Ag plus in brackets times Cl minus in brackets. Okay. If we were doing this for our BaCO3, don't forget that CO3 is a polyatomic ion. And so that would have, the entire ion in brackets. Some students might try to split that up, but remember, don't split up your polyatomic ions, keep them together. And so in this case, we would have Ba2 plus in brackets times our CO3 2 minus in brackets, okay? I did not make my dissociation equation on that one, but that's what the KSP would be. All right, your turn. You're going to try to create both the dissociation equation, right, what we have up there, and then also the KSP, but you're going to do that for our silver sulfide. Go ahead and do that in your notes, and then I'll call on you. All right, let's see how we did. We have got tellurium. What to start with? What is our dissociation equation? Mm-hmm. Good. Excellent job. Okay, now What do we have for our KSP, lead? Okay. I'm missing something. What am I missing? Missing one. Yeah, I'm missing the 2 right there. Okay, so make sure that we got our double or our coefficient turning into our exponent there. Good job. All right, so that's how we do those. Now, questions on that? Okay, so if we are going to distinguish between solubility and KSP, a couple things we want to remember: that there's a lot of possible values for solubility, right? Because it depends upon conditions besides just temperature. And remember that we're measuring this in things like, grams of solute per 100 grams of water, something like that at a particular temperature. So we might have the amount of liquid, might have the different type of substances that it's dissolving into, all that kind of stuff that could cause that to be different. But the KSP is only dependent upon our temperature. And remember that you're basically just multiplying the concentrations of your 2 ions. Remember that there's no unit for KSP, right? So while you have varying different types of units on here, okay, we have various different units here. We have no unit on our KSP. So they're different things, right? They both refer to things that are being dissolved, but one of them is telling us how much we could get dissolved in a particular amount. The other one is just giving us a relationship in terms of equilibrium, where these things might lie in terms of how much of each of those components is in the solution. Okay, so here is an example of calculating your KSP. Okay, the dissociation equation must be written, and so here we can see that we write a dissociation equation. This is very similar because of what we just did. The calcium 2 plus and the 2 fluorine ions. It tells us in this problem that we are going to find the KSP for calcium fluoride at 25 degrees Celsius if we have a saturated solution of calcium fluoride that has a concentration of 1.1 times 10 to the negative third molar. Now, if we are dealing with this quantity here, that is 0.011 molar of calcium fluoride. Okay? But I want you to remember what that means in terms of your ions. If I have that much calcium fluoride, that means that because every calcium fluoride breaks into 2 fluorines, 2 separate fluorine ions, that means that I have twice as much fluorine as I do calcium fluoride. Okay? Because every single one of those fluorines is, like the calcium fluorides, are breaking into 2 fluorines. So if my concentration of calcium fluoride is 0.0011 molar, then my concentration of fluorine ions is twice as much of that, 0.0022, right? All right, so it's important to understand what's happening here when I am writing my KSP as calcium fluoride. I have to double my fluorine's concentration first, and then I have to square it. So I have to do both things. So pay attention when you're doing these problems to how many ions you have when it breaks into solution so that you can have the right number that you put in here. If this had been something that broke into 3 ions, then I'd have a concentration of like a 0.0033, right? And so I have to make sure that this number here is going to be corresponding to the value I have on my coefficient. And then I also have to have an exponent applied to that. My KSP, notice, doesn't have a value there. It says 5.3 times 10 to the negative ninth. Is this a number bigger than 1 or less than 1? 5.3 times 10 to the negative ninth. Less than 1. Bigger than 0, but less than 1, right? And so remember, we said that if the K value was bigger than 1, that it was what favored? Product favored. And if it was less than 1, it was reactant favored, right? And so it makes sense to us if this is slightly soluble, right? This is pretty much insoluble, which means that this stuff is sticking together. It's not really dissolving much. And so this small number here says, yeah, you're basically staying calcium fluoride as a solid, and you're only getting a tiny little bit of a aqueous ions in here, okay? Because it's mostly going to be reactant favored. It's smaller than 1, so it's mostly going to be reactant favored. It's mostly going to be sticking here. Questions on that? Okay, I've got 2 problems for you to try now, okay? Ooh, that's not the button I meant to hit. Push. 2 problems for you to try so that you can see if you can do this. Question, go ahead.
So like when you double something, do you pay attention to like the charge and double it based on the charge, or like the coefficient?
So you are going to pay attention to the coefficient, okay? So for instance, in this case, my charge led to might give us a formula which is going to ultimately make us pay attention to the coefficient. Does that make sense? So that charge helps us figure out the coefficient, but when you're actually putting that into the problem, you want to pay attention to the coefficient. So they're kind of related, potentially. Question? KSP is just a particular type of KEQ that has to do with dissolved products. And so, yeah, it is basically the same thing as K. It's a KEQ. It's just EQ for dissolved products. And that's why we use the same formula and everything. Okay. It's not a reaction, but it is a K. Okay. So you've got 2 problems here. Let's see if you can solve them. The first one's a little bit easier than the second one, but let's see if we can get both of these problems solved in the next few minutes here. Where's the work? So for each of these, you should be showing the dissociation equation and then the KSP, and then plug in the values for your KSP components. Yeah.
After this, like, what do you plug in?
So yeah, so the concentrations, remember that's what brackets mean? The brackets mean the concentration of the substances. So if we look here, this tells us our concentration of the AgCl. And so now we can plug this number into the Ag and then into the Cl. Because when we split up AgCl, we split it up into the Ag part and the Cl part. And so you're going to have an equal amount of Ag as you do Cl, and they're both going to have that concentration. Mm-hmm. But on the next problem, it's not quite going to be the same. It's going to be a little bit harder.
Like a specific formula? Is it the KSP formula?
Yeah. So now what's the concentration of that? And so you plug that number
it's like
in.
half of that and you divide that by.
Not half of that, equal to that.
So they both have that exact thing.
They sure do. Why? Because for every one AgCl that breaks up, it breaks into one of these Ags plus one of these Cls, right? So whatever the concentration of this is, it's also the concentration of those. So if I had two of these, I'd have two Ags and two Cls, right? So whatever that number is there is going to be the same as the number that you have for the other two, for this one. Now for the next one, it's going to be a little bit different.
CO2 likes to be together.
That looks good. Okay, but that is great here, but you forgot that. Haven't done that part yet. You doubled it, which is what you needed to do, but you still have to square it. So it becomes doubled. And nope, you're totally great with what you have so far. You have to keep that number in there, and now you have to square it.
Was I right?
And now put the 2 on the outside. Now you go to the next.
Yeah. Is this the answer for the first one?
I'll have to go double check. I did not double check that.
Did I get this right?
Let's double check. Did you square this one?
Oh, it's squared.
Right, because you have to square it. No, you did great there, but you still have to square it. So don't forget, you need a 2 on there. Okay. So that was right for the first. Wait, where were you at? Yeah.
Which? I get 9.6.
Is that right? Let me double check one more time. Now I'm second guessing myself. Let's double check again. No, it's not right, Alessio. I lied to you. Did you have the right work? Let's double check if you have the right work. What did you plug into your concentrations for that and that?
The 1.3 times 10.
Okay, so if you did that, then you just did your math wrong. That should be your answer. Yes, that looks good. Yes, that looks good. That one. That one. I just feel like that's not quite right. Let's see what you did for your math on that one. Put in your numbers. Show me one more step of work so I can see what numbers you put into those values. Yes, and yes. Good job. That's a 5, right? Yeah. Okay. Not quite on this one. You need to double check your math on that one.
What's the temperature for?
So remember that temperature is the one thing that can change our K values. And so they're telling us that it's happening at 25 degrees Celsius. If they were to give us something at 27 degrees Celsius, then it would have a different answer. But what that would mean is that this would have a different solubility, right, at that temperature. So if they told us 27 degrees Celsius, it would be a different number that they would have given us here because there's going to be a different amount that can dissolve. So remember that this does not have units. When you come up with your final answer, you just leave it unitless. Uh-huh. And then this one's not quite right yet. 0.032 squared. You forgot to double it. All right, let me show you guys the answer since we're almost out of time here. So our first one, we just had to take our concentration of silver and our concentration of chlorine. They're both the same, and so we basically just get to multiply them by themselves, right, by each other. And so you end up with 1.7 times 10 to the negative 10th, no units. On this next one, you had to pay close attention to the fact that your 0.016 molar of PbCl2 turns into twice as much of your chlorine. And so you had to have the 0.032 plugged in first and then square it. Okay, so you get 2 chlorines for every 1 PbCl2, which means you get twice as much chlorine for the amount of PbCl that you started with. And so that is going to be squared. And so your final answer would be that. Any questions on that? Yeah, so sig figs in this case, we would do 2 sig figs for both of our answers. All right, good job, guys. Thank you so much for paying close attention and working hard. And now we can do those particular objectives.